Welcome to an interactive course designed to test and improve our knowledge of heat treatment. The topic of this course is to explain the issues of quenching under a protective atmosphere. Quenching in a protective atmosphere is one of the most common heat treatment processes. This variant is usually used for hardening parts in oil, but they can also be quenched in water, polymer, or salt. Each variant requires a different hardening bath, and sometimes a different furnace concept. The name of this type of processing is connected with the fact that the heating of the load, and in some cases also the quenching, takes place in a protective atmosphere, which has the task of protecting the parts from oxidation, or decarburization, or carburization. The choice of the quenching method depends on the steel grade and the required cooling rate for hardening to a martensitic structure. The fastest cooling can be achieved by quenching in water, slower in polymer, even slower in oil, and the slowest is in a salt bath. Protective atmosphere heat treatment equipment comes in various forms. There are many types of furnaces, but they can generally be divided into continuous furnaces and batch furnaces. Continuous furnaces are not entirely common for commercial heat treatment plants, so we will not describe them further here. Batch furnaces can be horizontal or vertical. In the case of horizontal furnaces, this can be a furnace concept with a single-sided loading or a through-flow solution. The picture shows a horizontal furnace with a single-sided loading, where in the first step the batch is loaded into the cold chamber. The entrance door is closed and the furnace is filled with endo-atmosphere. Then the door to the heating chamber is opened and the batch is transferred to hot zone to heat up to temperature. Once it is heated and the material is fully austenitized, the batch is taken out into the cold chamber, which is still under endo-atmosphere, and immersed in oil. Quenching is carried out. Once cooling is complete, the batch is taken out. In older types of furnaces, if the batch was in oil, it was not possible to load a new batch, and one had to wait for the end of quenching. In some more modern furnaces, however, there is a possibility that the loading of a new batch to the heating chamber is possible if the original batch is in an oil bath. This can save 30 to 60 minutes per cycle, which is the time waiting for the first charge to cool down. Examples of this arrangement are, for example, Ipsen, IVA, Icolin, or AFC Holcroft furnaces. A typical accompanying feature of this type of furnace is that the loading and unloading loader is only on one side of the furnace. The disadvantage of this solution is most apparent when normalizing is performed in the furnace. In this case, the charge is not cooled in an oil bath, but in a cold chamber with free or forced atmosphere flow. The waiting times for cooling down after normalizing are then an hour or more, and during this time, a new batch cannot be loaded. Another furnace design, which is typical today, is a continuous solution. The batch is loaded into the heating chamber from one side. There it is, heated to the austenitization temperature. The middle door is opened, and the batch is taken out into the cold chamber. It is then immersed in oil for quenching. As soon as the middle door is closed behind it, another batch can be loaded into the heating chamber. The cold chamber is again permanently under the endo-atmosphere. After quenching, the batch is taken out through the unloading door to the other side of the furnace. This arrangement allows for significantly higher utilization of the equipment. Since the cooling time of the batch in the oil bath is usually shorter than the time for heating the new batch, the furnace can perform efficient quenching in a cycle of 1 hour. The loader is on one side of the furnace, the unloading carriage on the other side. Both types of equipment are easy to distinguish at first glance, as the continuous solution has two operating loaders. The main representative of this type of furnace are Ipsen furnaces marked TQ. However, there is also a solution with 3 chambers, where the furnace is loaded through the first preheating chamber. Then the batch is moved to the middle chamber with final heating, and then to the quenching chamber with an oil bath. The advantages will be seen both in hardening and in carburizing. When quenching in the first chamber, we preheat the batch to, for example, 500 Celsius, and as a result of this preheating, the heating process in the middle chamber is significantly shorter. In the case of carburizing, this middle chamber, by being permanently at temperature and permanently saturated to the appropriate carbon potential, significantly speeds up the carburizing process. In both cases, the use of the furnace increases significantly. This solution allows you to have up to 3 batches in the furnace at the same time. What it looks like to work with such a multi-purpose furnace for oil quenching can be seen in the video. It is a one-sided loading furnace, where the batch is loaded and unloaded to the same side. The unloading door opens, and the batch goes into the cold chamber through a flame screen. It is ignited by the safety burners at the bottom of the door when the door opens slightly and the endo-atmosphere begins to penetrate outside the furnace. This guarantees safety against a possible explosion and prevents air from entering the furnace. Once the batch is in the furnace, the door closes and the actual process begins. What is not visible is that the batch moves further into the heating chamber and is heated there to austenitization temperature. After reaching the temperature, the batch is returned to the cold chamber and quenched into an oil bath that is below the loading level. The batch is then lifted in the furnace to the level for unloading. The unloading door is opened again, the flame screen is lit again, and the batch is taken out. In the next step, it goes to the washing machine, where it gets rid of the quenching oil. This is the end of the hardening or carburizing process, but in reality, it is transported to the tempering furnace. Only when the batch is tempered can leave the line for multi-purpose heat treatment. Another solution are furnaces from Swiss manufacturers, either Solo or Codere. This is a vertical bell furnace design, where mobile heating chambers are located in the upper part of the device, and various hardening baths in the lower part, from oil, water, or polymer to salt. The line usually includes a washing machine or tempering furnace. Equipment of this type is very flexible with many options for arranging the line into the required configuration. The equipment can make hardening, carburizing, carbonitriding, but modules for nitriding or nitrocarburizing or chambers for annealing processes can also be added. This video shows another example of the device. This is a vertical solution for a furnace for hardening under a protective atmosphere from the Codere company with the designation System 250. The line consists of one high-temperature chamber for heating to the quenching temperature or for carburizing, a washing machine, and a tempering furnace. Everything is arranged so that the operation of the line is completely automatic and unattended. In the first step, the robot loads the batch into the line. In the next step, the batch is then into the heating chamber and heated to the austenitizing temperature. If it is only hardening, nitrogen can be used as the basic inert protective atmosphere. If it is carburizing, then the device uses nitrogen, methanol atmosphere, and, for example, propane to regulate the carbon potential. This is followed by quenching in oil, but the device can also be equipped with quenching baths in water or in salt or quenching in nitrogen. The next step includes washing and tempering. After the robot removes the batch from the line, the entire production process is complete. This video shows that solutions for hardening in a protective atmosphere are very diverse, but in many cases very effective. What do all these furnaces have in common? It is a protective atmosphere that prevents possible oxidation. This is undesirable because it significantly reduces the mechanical properties of the steel, both tensile and shear strength, and also worsens the fatigue properties. The oxides that form are formed preferentially along the grain boundary and are a source of defects that can lead to catastrophic damage to parts. The protective atmosphere therefore prevents oxidation of parts during heating, austenitization soak, and during quenching, and is present both in the heating chamber and above the oil bath. Since the furnaces are atmospheric, they operate with a slight gas overpressure, and thus prevent air from penetrating into the working space. Flame screens then protect the furnace and the batch from air entering the furnace when the door is opened. In addition to oxidation, the second important reason for using a protective atmosphere is that the natural atmosphere, air, has a decarburizing effect and draws carbon from the surface of the steel. This phenomenon is undesirable because it changes its properties. Therefore, in order to prevent decarburization or carburization of the surface of steel parts during heating and holding at the austenitizing temperature, the atmosphere in the furnace should have a carbon potential Cp, which represents an equilibrium state between the steel surface and the atmosphere. If the carbon potential of the atmosphere is less than the carbon content of the steel, decarburization occurs. If it is greater, carburization occurs. Since each steel has a different carbon content, from 0.1% to 2.1%, the CP control process must be sufficiently flexible from process to process, and at the same time stable within the process. The aim of the protective atmosphere during the heat treatment process is therefore to prevent oxidation due to atmospheric oxygen, while at the same time creating a balance between the carbon in the steel and the carbon in the atmosphere of the working chamber where the parts are heated for hardening. Theoretically, an atmosphere of nitrogen would be sufficient for hardening. It is neutral gas and has no effect on carbon in steel, and would be sufficient as a protection against oxidation. However, this atmosphere is used more for tempering or annealing, but not for hardening. This is because hardening in multi-purpose furnaces are also designed for carburizing and carbonitriding, and it would be very difficult to control the carbon potential. Therefore, for reasons of flexibility, the most commonly used gas for hardening is the atmosphere of endo. The endo atmosphere is usually formed in an external generator from a mixture of natural gas and air, but other hydrocarbons can also be used, propane or methane. However, there is also a variant where it can be created directly in the furnace, by injection and thermal decomposition of methanol supplied to the furnace together with nitrogen in a ratio of 60% methanol and 40% nitrogen. All methods are possible, depending only on whether the heat treatment shop is equipped with a sufficient supply of natural gas or on the ability to implement appropriate safety measures, because methanol is a highly poisonous, flammable liquid. Economic criteria are also decisive. The methanol atmosphere is 50% more expensive than endo atmosphere created in generator. If we want to increase the potential for this atmosphere, we add hydrocarbons. If we want to reduce it, then we allow air. A typical endo atmosphere from natural gas contains approximately 40% nitrogen, 40% hydrogen, 20% carbon monoxide, 0.3% carbon dioxide, and 0.7% water vapor. In the case of using propane or methane, the chemical composition is partially different, but the CO2 content is decisive. The basic carbon potential of the endo atmosphere is 0.3% and corresponds to a dew point of 5 to 8 Celsius. In such an atmosphere, however, it is only possible to harden steels with a carbon content of approximately 0.3%, without the carbon content of the steel being affected by the atmosphere. However, If we want to process steels with a higher carbon content, it is necessary to increase the carbon potential of CP. This can be done by adding some hydrocarbon, most often natural gas or propane. Carbon activity, or carbon potential, can be measured and regulated using the dew point of the atmosphere, CO2 analysis, or an oxygen probe. For a layman, it looks wild, but everything is measured for us by appropriate devices or probes. The output is an electrical signal in millivolts, which is connected to a standard PID controller. An action element, for example a flow meter, is connected to it, and it emits more or less carbonizing gas, such as propane, methane, or natural gas. However, we cannot forget the classic method of measuring CP using a test foil. Even though it is the most accurate method, with an accuracy of carbon determination of 0.01%, its use is intended rather for verifying the accuracy of other devices. The principle of the method is that a precisely weighed foil, with a defined carbon content, usually 0.1%, is placed in a heated and saturated furnace. After saturation, the foil is weighed again and the carbon content is calculated. This data then corresponds to the CP in the furnace. The condition for its use, however, is that the furnace has a hole for inserting the holder with the foil. Inserting the foil is not entirely simple either, and requires not only equipment, but also experience. If an oxygen probe is verified in this way, then the foil test should also be carried out near it so as to best express the potential of the probes. Therefore, for the furnace to comply with recognized standards such as CQY9, the carbon potential control must be able to maintain this parameter with a deviation of 0.05%. For each measured quantity, there are already developed curves showing the dependence of the carbon potential on the dew point, on the CO2 content, or on the size of the signal in millivolts from the oxygen probe. Based on this, the instruments then evaluate whether more or less added hydrocarbon is needed in the case of the endo-atmosphere, or hydrocarbon and air in the case of the methanol atmosphere. Dew point or carbon dioxide measurements are made outside the furnace, on an atmospheric sample taken from the furnace, while an oxygen probe is inserted directly into the working area, and thus measures the carbon potential directly in the furnace. The most commonly used method today is to measure CP using an oxygen probe. The oxygen probe consists of a zirconium oxide oxygen sensor, a thermocouple, a protective tube, and a head. Zirconium oxide, ZrO2, is a solid electrolyte that conducts oxygen ions at temperatures above 700 degrees Celsius. Ionic conductivity causes a voltage between the inner and outer surfaces of the sensor. The magnitude of the voltage depends on the temperature of the sensor and the ratio of the partial pressures of oxygen on the reference and measuring sides of the solid electrolyte. Reference air of sufficient purity is therefore supplied to the probe. The oxygen content in it is compared with the oxygen content in the atmosphere in the furnace. In order for the furnace to perform heat treatment processes, it must be in a calibrated state. It must have the necessary control sensors for measuring temperature, at least one control thermocouple and one safety thermocouple. It must show the prescribed uniformity of the temperature according to AMS 2750 or CQY9. The furnace thermocouples must be checked for measurement accuracy using the SAT test, and for measuring and regulating the carbon potential, it must have a control signal, usually from an oxygen probe. If we are going to work for the automotive industry, then there is also a requirement for the supervisory measurement, checking that the CP value is real, does not deviate from the requirement, and does not indicate a discrepancy between the carbon potential from the reference and control sources. According to CQY9, This monitoring or supervisory source can be a duplicate oxygen probe, which is the preferred and simplest solution, or another physically different source, such as a CO2 analyzer, dew point, or foil test, giving sufficiently accurate results at the required periodicity. However, it is necessary to take into account that if we use, for example, a gas analyzer for monitoring measurements, and we also perform carburizing in the furnace, then we must also accept that its daily calibration is required. A record of monitoring all this data is then required for each process. Maintaining a heat treatment device with a protective atmosphere is not at all easy and requires high qualification of the personnel, especially on the maintenance team. In order for the device to be released for applications in the automotive or aerospace industry, it must meet the following requirements. It must be in the furnace accuracy class according to the specification for the given application. According to CQI 9, as well as according to the American Standard AMS 2759, it is usually furnace class 5 with a temperature uniformity of ±14 Celsius. The measurement of TUS, Temperature Uniformity Survey, and the measurement of temperature accuracy SAT, System Accuracy Test, must be carried out in the periodicity according to AMS 2750 in the current version, or according to another relevant specification such as CQI 9. The furnace must be equipped with a carbon potential measurement and its supervisory control, with calibrations in the periodicity, according to CQI 9, once every 3 months. The behavior of the control probe is checked daily using the supervisory method. If the CP monitoring is performed by a gas analyzer, then its calibration is required once a week if we only perform quenching processes, and daily if we also perform carburizing. All data from temperature sensors, as well as from carbon potential meters, must be continuously monitored and recorded. Inspection and maintenance of the oil bath, its cleanliness, periodic or continuous filtration, inspection for oil contamination with water with a maximum content of 0.1% water at a frequency according to CQI 9, namely once every 6 months, must be ensured. As part of the inspection, the water content, the amount of solid impurities, viscosity, cooling capacity, acidity, and flash point should be measured. Data on the oil temperature or level control must be continuously monitored with appropriate alarms. It must be ensured that the time of the batch transfer between the heating chamber and the quenching oil bath, from opening the door to capturing the entire batch in the oil, is within a defined time. And for some applications, such as the aerospace industry, it is essential to achieve this in 20 seconds. In general, it can be said that the requirements for the equipment are constantly increasing. Quality management systems of the ISO 9001 type are now only a basic condition, but not sufficient, and ISO TS 16949 for the automotive industry is gradually increasing its requirements using CQI 9 so that it is specifically aimed at quality according to NADCAP, which is quality for the aerospace industry. The disadvantage of multi-purpose furnaces is the impossibility of placing a thermocouple in the batch, which would control the rise in temperature of the parts, and which would visualize and standardize the time of austenitization. The reason is the mobility of the batch during the process and its transitions between individual chambers. Data loggers with wireless signal transmission outside the furnace are emerging as a certain solution for the future. Given the measurement temperature, however, the problem of protecting the measuring device against overheating at the austenitizing temperature still persists. Insulation materials do not yet allow minimizing the size of insulation box, and therefore the size of the measuring device increases with increasing temperature, and therefore its volume shared in the batch. The figure shows that the time the device remains in the furnace at a temperature of 800 Celsius can now be up to 8 hours, but the size of the protective box already exceeds the purpose of use. However, this is an interesting option for modeling the heat treatment process with respect to the batch in the case of repeated production, and the main criterion is the economy of the process. In this case, we need the data logger's protective box to protect the device during a 3 to 4 hour cycle at a temperature. However, we will definitely use this device to measure the temperature uniformity in the furnace, to classify the furnace into the accuracy class, according to CQY9 or AMS 2750, in the periodicity, according to these standards. When determining heating times, we usually rely on empirical calculations based on heating theory. We do not have an accurate temperature measurement because we do not have a load thermocouple in the batch. The ideal temperature profile is shown in the figure. It consists of the heating phase, heating through whole cross-section, and soaking at temperature. The heating time is the time from when the batch is loaded into the heating chamber until the furnace rises to the desired temperature, set point. In this phase, we have an overview of when the furnace temperature has reached the desired value. But we no longer see the moment when the surface of the batch has also reached this temperature. In this heating phase, it also depends on whether we place the batch in the furnace at a temperature lower than the set point, or whether we only heat up the temperature drop caused by the introduction of a cold batch, or whether we preheat the furnace in advance, for example by 50 degrees Celsius, and after loading the batch, we simply wait for the furnace temperature to drop to the set value. All variants are possible if the processing result is okay. In any case, this heating phase is not fully under our control, and we have to rely on our experience and historical data. This first period is followed by the next phase, when, depending on the size of the part, the structuring of the batch and its density, loading plan, it is necessary to bring all parts in the entire cross-section to the austenitizing temperature. This is again the stage where we would need a thermocouple to measure the temperature at the core of the piece, like in single-chamber vacuum furnaces. But since we do not have one, we must be helped by empirical determination of this stage with regard to the heat transfer between the furnace and the load, the thermal conductivity of the material, the degree of shielding, as well as with regard to long-term statistical monitoring of the treatment results. The final heating phase is the soaking time at the austenitizing temperature. This is usually, in the case of hardening in multipurpose furnaces, 30 minutes. In the case of carburizing, the moment when whole batch is heated to set point temperature, and we can start with carburizing. Here it depends on the material grade, or its sensibility to grain size grow, but the heat treatment technologist will also have a decisive say. Where we do not have a process data verified by testing, we can use this graph. It expresses the relationship between the heating time and the characteristic dimension of the part. The larger the diameter or size of the product, the longer the time we will have to choose. The diagram should therefore be taken as a guide, and applies only to one ideal piece. To determine the heating time of the entire batch, it is necessary to take into account other parameters, but, above all, the results of the evaluation of the resulting structure, hardness, or carburizing depth of already tuned processes, and either apply the process parameters in full or modify them and adapt them to the new batch. Since heat treatment is one of the so-called special processes, which are characterized by the fact that the path to ensuring the customer requirement can be different, the result will be important to us. Another form of graphical presentation of the holding time setting, including the 30-minute austenitization time, is shown in this graph. The operator selects the maximum characteristic dimension of the part on the horizontal axis. The curve for a given furnace temperature, in this case 950 degrees Celsius, and reads the time on the vertical axis. This time is multiplied by a coefficient of batch density and part geometry, usually in the range of 1 to 2. Another way of prescribing soaking time is in the AMSH 6875 standard for the aerospace industry. This standard specifies a minimum holding time setting according to a table, depending on the size of the parts. The following rules apply. The holding time must not start counting down before the furnace reaches the required temperature -6 degrees Celsius below the set value. The soaking time is given for a batch of one piece. The time for the entire batch must be extended. The holding time must not exceed twice the table value. The smallest profile dimension is always taken to select the critical thickness, T. This value is multiplied by the shape coefficient. For round parts, the critical dimension is the diameter and the coefficient is 1. For square parts, 1.25. For flat profiles, 1.5 of the narrower side. For pipes, it is double wall thickness, etc. Each heat treatment facility has a different approach to this problem based on long-term experience and evaluation of heat treatment results. However, all of these methods are empirical and cannot fully replace measurements of T-surface and T-core directly placed in the batch. However, for repeated processes, they can be set accurately enough to ensure that the heat treatment is carried out in accordance with standards and requirements and meets reproducibility and reliability. Unlike vacuum, when preparing a batch for heat treatment in multi-purpose furnaces, it is necessary to have in mind two parameters that we need for proper processing: the temperature and carbon potential, CP. For complete batches, when we process one material grade and one type of part, this is not a problem. We insert the processing parameters into the routing, and then, if the results do not deviate from the specification, we repeat it permanently. However, it is different for mixed batches in commercial heat treatment. There, we have to consider what criteria must be met so that parts of different shapes, made of different steel grades, can be processed in one batch. The picture shows some instructions on how to do this while maintaining the optimal approach. In practical use, it is necessary to categorize steels into groups according to austenitization temperature and carbon content. In our example, there are 7 groups of materials that can be heat-treated together. It is up to the heat treater how it organizes these processes, but it is always necessary to remember that all parts should be always proceed according to the usual procedures. In other words, it should not deviate from the relevant standards. Another criterion is the size and shape of the parts. In addition to the temperature and CP, it must also be met that their heating has approximately the same behavior and that all parts in the batch are completely austenitized within the set time. So how do we determine the above parameters? We must first find out something about the steel we are to process. For example, we have the task of hardening tool steel 1.2842 to a hardness of 60 to 62 HRC in a multipurpose furnace with a protective atmosphere. Since the working atmosphere in the furnace is endo, we must first find out the carbon content and the recommended austenitization temperature. From the chemical composition, we can read that the carbon content is 0.85 to 0.95%. We therefore need an atmosphere with a carbon potential of approximately 0.9%. The second piece of information is the austenitization temperature. This should be 780 to 820 Celsius. For small, tiny parts, we should choose lower temperatures, and for large parts, higher temperatures. Since our parts are large with a thickness of over 30 millimeters, we will decide on the highest allowed temperature of 820 degrees Celsius. The hardening environment is determined by the furnace we have available. In our case, with an oil bath and Durexol W72 quenching oil with a high cooling rate and working temperatures from 50 to 130 Celsius. We will choose the temperature of the oil bath according to the characteristics of the parts and the possibilities of the oil. Since we want low deformations, we will increase the oil temperature to 120 Celsius, and we will also prescribe the oil agitation mode, its speed, or possibly the direction of flow. So we now have all the necessary heat treatment parameters. The carbon potential will therefore be 0.9, the quenching temperature 820 Celsius, and the oil bath temperature 120 Celsius. We will set the heating time according to our experience with the given furnace. The holding time for austenitizing will be 30 minutes. The holding time in the quenching bath will also be 30 minutes. The oil agitation will be intensive for the first 5 minutes, the remaining time slow. However, the setting range depends on the furnace capabilities and batch parameters and can be very individual. The resulting work procedure will be specified in the production order, for example, in this way. It looks complicated at first glance, but in reality, since the heat treatment plant usually involves repetitive activities, we select the work instructions from the archive of previously performed processing, and the furnace program is also stored in the furnace memory. The table shows a set of general routings for material 1.2842 for various dimensions of parts. For each characteristic dimension, in this case dia 20 or dia 40 millimeters, there is a reference to the furnace program number in the routing, and it differs only in the selection of holding time at temperature depending on the dimensions of the parts and batch assembly. Other program parameters, such as carbon potential, austenitizing temperature, oil temperature, agitation, will be the same. We will proceed similarly when processing 42 chromium molybdenum 4 steel intended for quenching and tempering. The carbon content should be in the range of 0.38 to 0.45%. We will choose the carbon potential at the upper limit of the range 0.45. The recommended quenching temperature is 820 to 860 Celsius. However, since the customer has prescribed quenching from a temperature of 860 Celsius, we have no choice and must adhere to this temperature. Given that it will be a batch weighing almost 400 kilograms, consisting of parts of the same characteristic dimension of 80 millimeters, the heating time will be determined according to our own auxiliary table at 90 minutes, with regard to the composition of the batch then, with a coefficient of 2, a total of 180 minutes. We will also add the time for austenitization of 30 minutes, and we have the resulting time from loading the batch into the furnace to opening the unloading door and subsequent quenching of 210 minutes. The last task is then to choose the oil temperature, the speed and method of agitation of the oil bath, and the time the batch remains in the oil to complete the martensitic transformation. Even if we will quench again in Durexol W72, in this case we will choose the oil temperature of 80 degrees Celsius and set the remaining parameters according to our experience. The resulting recipe looks like this one. The abbreviation AQ plus T stands for atmosphere quenching plus tempering, and the process parameters are as follows. The entire record in this form is adapted to the ERP system, where we assign a routing to the product. The data in the title is used for quick filtering in the database. Each heat treater can find their own way of identifying the process in the ERP system, but we must always keep in mind the searchability and traceability of the required routing. That is why it is necessary to think about change management and record it. However, it is necessary to state that in practice, only the result can show the correctness of the parameter settings. This means structure, hardness, tensile strength, etc. After the testing process is complete, it is necessary to measure all required properties in the entire batch volume and only then approve the parameters. The entire process flow is described in a procedure called APQP, Advanced Product Quality Planning. Special attention needs to be paid to the quenching oil. It is used to intensively cool the batch so that it hardens. The oil bath is heated to a temperature depending on the type of oil and the processing requirements, but it is usually around 80 degrees Celsius. The higher the oil temperature, the lower the deformations can be, but the lower the cooling capacity of the bath. The highest temperature of the oil bath is tied to the furnace design, usually up to 150 to 160 Celsius maximum. However, it is necessary to choose oils with a higher working temperature. Oils have different viscosities, and accordingly, fast cooling or slow cooling oils can be selected. The problem is that the oil bath contains a large amount of oil, in the order of cubic meters, and once we decide on an oil, it is difficult to change it. If we have several multi-purpose furnaces and a diverse range of processing, we can have a different oil in each quenching furnace. However, the oils cannot usually be completely separated in operation, because even for several furnaces, we usually only have one washer, and there they are mixed. Therefore, the choice of oil must always be carefully considered with regard to the expected range and the layout of the heat treatment operation. The safety of the oil bath is also an important parameter. In terms of emergencies in the heat treatment operation, this is the most common cause of fire. All oils have a flash point of around 200 degrees Celsius. If a hot batch heated to the quenching temperature is immersed in oil, the oil bath may ignite. In multi-purpose furnaces, the most common cause is a leak in the furnace and the presence of air above the oil bath, impurities in the oil, and especially the presence of water in the oil. The larger is the surface of the parts in the batch, especially for small parts, the more significant this problem is. It is therefore necessary to maintain an oxygen-free environment above the oil bath at the time of quenching, which is why this space must be well gassed with an endo-atmosphere. However, this contains almost 40% hydrogen. Therefore, the furnace must be tight, and there must be a permanent, controllable overpressure of 30 to 50 millibar inside the furnace. For this reason, there is a burnout flap on the furnace in the quenching chamber, which ensures that this overpressure is maintained. The oil bath must be well cooled, so that heat is quickly removed from the batch and at the same time the oil does not overheat. This is also helped by the intensive agitation of the oil bath. The quenched batch has a layer of oil on its surface. However, because when unloading from the cold chamber, this batch passes through a flame screen, which ensures the burnout of the endo-atmosphere. It may happen that the oil on the parts ignites when unloading a batch of small parts with a large surface area. In some cases, this is solved by adding a nitrogen screen at the outlet from the furnace, which prevents the formation of a flame. These photos show how this can turn out. Safety at work on multi-purpose furnaces, especially in terms of a possible oil bath fire, is very important, and neglecting it can endanger the entire heat treatment plant. Special attention must be paid to regular monitoring of the oil bath for water content. In terms of potential risks, this risk is the most significant. Under conditions of high temperature, pressure of superheated water vapor, and the presence of free metal elements, oxygen is reduced from the water molecule to form metal oxides and free hydrogen. Subsequently, hydrogen recombines with oxygen. Another reaction that takes place in the resulting gaseous environment is the reaction of carbon and water to form carbon monoxide and hydrogen. Carbon monoxide then binds with additional oxygen and forms carbon dioxide. Both of these reactions of hydrogen with oxygen or carbon are exothermic, when a large amount of energy is released. You can see an example in the video, where an explosion occurs when hot slag is taken out into a snowfield. Exactly the same thing can happen if a hot charge of oil containing more than 0.1% water is immersed. Long-term used oil also contains metal microparticles or carbon in the form of soot, which also participate in the exothermic reaction. Therefore, it is necessary to filter the oil bath regularly and remove this type of impurity. Maintenance of the oil bath by filtration or sedimentation with subsequent removal of sludge is therefore very important for the safety of heat treatment plant. It is usually carried out during summer or winter shutdowns. However, continuous filtration is also a solution. This removes microparticles and impurities from the oil continuously. These can both reduce the cooling efficiency of the oil and can have a similar effect to water. In the continuous filtration mode, a steel mesh with a density of 10 micron can be used. If it is necessary to work with filters with a higher density, for example 1 micron, then textile filters must be used. However, these can only work effectively up to an oil temperature of 80 Celsius. In such a case, filtering is not possible during quenching, when the oil temperature can rise above this limit. Technical solutions vary. Usually, a pair of these filters are installed in parallel, allowing the filters to be cleaned continuously during operation while the filtration is running. As already mentioned, Solo or Codere type bell furnaces allow polymer or salt quenching. Polymer quenching is justified mainly in induction hardening, but it can also be used in bulk quenching. Polymer has the property that it allows the cooling rate to be slowed down during water quenching. Depending on the type of polymer, a cooling rate that is up to the level of fast oil can be obtained. The change in the cooling rate is determined both by the type of polymer and by its concentration in the bath. The advantages are as follows. Solutions and concentrates are non-flammable. No oil mist or harmful fumes are produced during quenching. No flame is generated during quenching. At higher tempering temperatures, washing is not required. The polymer decomposes into carbon dioxide, nitrogen, and water vapor. The purchase price of the quenching bath is significantly lower than with oil. The disadvantages are higher deformations, although they may be lower than with water quenching, and bath maintenance is also complex. The greatest danger is biological degradation. This type of equipment also allows for salt bath hardening. Liquid salt bath can reduce distortions, both because of the high temperature of the salt bath and because the heat from the quenched parts is removed by direct contact with the bath. The heat dissipation is uniform, and therefore deformations are usually lower than with other hardening methods. Usually, AS 140 salt is used with working temperatures of 150 to 550 Celsius. However, salt can only be used for hardening parts from temperatures lower than 950 Celsius. The salt bath contains up to 14% potassium cyanide and is therefore a problem with work safety and ecology. Although it is a relatively cheap processing method, ecological aspects, on the contrary, make this technology significantly more expensive. It is advantageously used for bainitic hardening, austemper, when the bath temperature is above martensite start in the range of 200 to 400 Celsius. And now let's do a short recap. Processes under protective atmosphere have an irreplaceable role in hardening processes. The protective atmosphere is usually an endotype atmosphere, formed either from natural gas or other hydrocarbon with air, or formed from methanol and nitrogen. The main objective of protective atmosphere is to prevent oxidation and to allow CP to be controlled as needed. CP is measured either by dew point measurement or by O2 measurement or oxygen probe. For process validation for the automotive industry, according to CQI-9, the CP check must be duplicated to ensure that the CP does not deviate from the requirement. The hardening equipment must comply with AMS 2750 for temperature control and should meet the conditions for furnace class 5 with a temperature uniformity of ± 14 degrees Celsius. Oil bath maintenance is important to ensure that quenching conditions are safe and reproducible. It is important to have quality cooling and swirling of the oil during quenching, to check the oil for impurities with possible periodic or permanent filtration, and to check the oil for water content as a source of potential accidents. The choice of heating time, preheating, and temperature holding time depends either on empirical calculations or on practical verification of the sampling charges for the customer. In some cases, it is advantageous to use polymer or salt hardening. Each of these methods has its justification for certain applications. The course on steel's tempering is over. It includes my many years of experience and practice. However, the issues can be very complex and extensive, and may not exactly match your experience. If you have any comments or suggestions for improving the course, please send them to the contact listed. My goal is for the courses to provide essential information for heat treatment employees at all levels so that they can continuously improve. The level of content is therefore adapted to allow both existing employees and new employees who do not have knowledge in the field to take part in this course. Based on these comments, I will improve and expand the courses so that they are a real benefit to everyone. As you have probably noticed, the course was not voiced by me, but by the great speech generator 11 Labs. Thanks to him, my English will also be understandable. So thank you also to Bill and his voice for his contribution to the field of heat treatment. What you saw as a video on YouTube is just a picture of what is created in Adobe Captivate as an e-learning course. It is available on my website, jstconsultancy.cz. You can access it for €20 for 1 week, €40 for 1 month, or €60 for 1 year. The course is created in HTML5 format. However, it can also be exported to SCORM 1.2 format, which stands for Shareable Content Object Reference Model. Other formats are possible for different LMS systems. You can order this form at my email address, and you will receive the complete course in HTML5 code and a perpetual license for €200 per course. The compressed zip file will be 50 to 200 megabytes in size, depending on the content of the course. You can then install this file in your corporate cloud or in Moodle LMS 5.0, on SharePoint or in the HR module of your ERP system, such as SAP, which can communicate with a learning management system, LMS, that meets the LMS specification. In this case, you will be able to prepare a training plan for each employee, including an evaluation of its implementation and success rate. Each course contains a test with many questions, and the output is a certificate of successful completion of the course. You can archive these certificates and use them for employee motivational rewards. The advantages of e-learning are obvious. The employee does not have to go anywhere. They can complete the course anywhere, on a computer, tablet, or even a phone, at work, on vacation, or even at home. And you will be sure that they have the necessary knowledge to understand what is happening in the heat treatment operation. I do not know of any disadvantages, so I just hope that these courses will serve you and be useful to you. And what is my vision for the future? You can see this in this process map. So far, 16 have been created in Czech and English, and I will gradually add new ones, depending on their importance in the life of the heat treatment operation. I don't know if the courses are perfect, but I'm sure it's a promising form of education that we shouldn't ignore.